so now let's do some basic applications of vectors. We're going to begin with vectors as velocity. So if an object's motion can be described by the velocity vector v, which is v1 and v2 as its components, then the object's speed is the magnitude of that vector. And the object's direction is theta, where the tangent of theta is equal to v2 over v1. So let me draw a picture real quick, because this is based in basic geometry that you know. So if you have a vector v coming out like that, right? If that's your vector v, it has two components, right? It has a v1, which is right here, and a v2, which is right here. Those are the components, the x and the y. They form a right angle with the x-axis, and they have an angle theta right here. Now the magnitude of v is literally the length of that vector. All right, the tangent, right, is the tangent of the angle is the opposite over the adjacent. So it's v2 divided by v1, just like we would expect from geometry. And one interesting side note of that, this is just a little note, it's not critical at this stage, but we'll need it later. The cosine of your angle is the v1 component, right? The horizontal, the adjacent component, divided by the magnitude of v, right? So that means that v1 is the magnitude of v times the cosine of theta. And similarly, the sine of theta is v2 divided by the magnitude of v. And that means that v2 is the magnitude of v times the sine of theta. All right, so let's put it together. If you are driving 50 miles per hour in a direction that is 20 degrees north of due west, express your velocity as a vector in standard position. Assume the usual orientation of the directional axes with the positive y direction representing the direct north. Okay, so you're going to drive 50 miles per hour in a direction that is 20 degrees north of due west. So let's draw an axis here. North of due west means you have an angle here that is 20 degrees. So this angle right here is 20 degrees north of due west, which is right here, the negative x-axis. And they want a vector here. Okay, so if we want a vector, we need to know the v1 and the v2, right? So v1 and v2, if we had them together, would give us our piece. Now the problem is that we can't use the angle 20 degrees because 20 degrees is north of west, which is not how we orient angles. We do know the size, by the way, of this vector, right? So this vector v has a size of 50. So the magnitude of vector is 50 because it's 50 miles per hour. So that's the magnitude. No problem. But we don't know the angles, and we can't make a vector out of it. So we're going to have to use these two pieces right here that I just added to the definition. Okay, so v1 would be the magnitude of v times the cosine of our angle. And the magnitude of v is easy, that's 50. But the angle is not 20. Because your angle has to be from the positive x-axis, like how we always do angles in a counterclockwise direction. So that would be 160 degrees, because of course these are supplementary angles to make a straight line. There's a term you hadn't heard in a while. So this is 160 degrees right here. And then v2 would be the magnitude of v times the sine of theta. So that would be 50 sine of 160 degrees. And then, of course, we probably want just some decimal approximation. So I would grab Desmos or I would grab Maple and make it come up with it for me. And just because I know Maple is more difficult, I'm going to do Maple. So I'm going to start with a convert command. I'm not even going to copy and paste. Convert, and I want to convert 160 degrees to radians. And for the record, I can actually call that something. I can call it a letter, say like A1 colon equals. Right. So that'll call that. So now it knows A1 is that angle. And so then I can say to it, all right, well then find me 50 times the cosine of A1. And it does it. And then if I want a decimal for that, I could do 50.0 perhaps times it. Nope, it's not going to do it. Well, then I'm going to have to do the approximation thing, which is fine. I'm just making this larger so you can see it. There we go. I don't like how small the outputs are. I know there's a way to change it, but there we go. So it says it's negative 46.984. All right, and then I would do the same thing for sine. So I would say 50 times the sine of A1. And it gives me that. And then again, I can do a decimal approximation and say I want 5 decimal places. And it tells me that it's 17.101. So my angle, or my vector pieces, components, are negative 46.984 and 17.101. All right, so that will become my vector v. So vector v is negative 46 point, it's approximately, negative 46.984 and 17.101. You'll notice that it's in quadrant 2. All right, now what about this example? Let's describe the speed and direction of an object with velocity v, which is negative 22.5 I and negative 26.8 j. Interesting. So let's think about this for a second. Because it's negative I and negative j, that means that it's actually going down into quadrant 3, right? Because we are over negative 22.5 and we're down negative 26.8. Sorry, there's a point in there. It got lost. So let me draw that again. There we go. Okay, so we need to find the speed and direction. Now, speed is actually relatively easy. Speed is just the magnitude of the velocity vector. So that would be the square root of negative 22.5 squared plus negative 26.8 squared. I'll grab Maple. So square root is a command. It's also in the palette. You can find it. It's in the expressions palette, I believe. So parentheses negative 22.5 squared plus parentheses negative 26.8 squared. There are other ways to do this, but this will be quick and easy. So we got 34.99. So for example, we could call the vector v and then have it find the magnitude for us, et cetera, et cetera. So it'd be 34.99. And if we assume our standard units, it'd be meters per second. Okay, so this would be 34.99 meters per second, or miles per hour. I'm just assuming meters per second. That's pretty standard. Okay, now to get the direction, we're going to need the angle. So we're going to need theta. So that's going to be a little trickier. So remember that the tangent of theta is v2 over v1, which in our case would be negative 26.8 divided by negative 22.5. Okay, so that means that theta would be the arctangent of negative 26.8 over negative 22.5, sort of. So at this point, you have to remember pre-calc. There's some issues with theta. I think I'm actually, I could do this in Maple. Arctan of negative 26.8 divided by negative 22.5. However, it's not going to like me. It's going to do it in radians. So it's going to give me the angle in radians, which isn't really what I'm looking for. So I can tell it to convert that radians to degrees. So, and I want to show you a little trick when I do this. So if I want to say, hey, convert that number I just found. If you look over on the right, that number has a label. See where it says number 13? That's the label for that output. So I could actually copy and paste this number and say, hey, convert that. Convert it to degrees. I believe this will work. Yes, it does. 49.984. That's correct. So that's what we want. Or, just see this. I can say to it, convert as a command, and I can say insert the label. So convert, and I want to convert number 13. So insert label. The identifier is 13, and it'll take 13 and change it to degrees. There you go. Same answer. So you can use the label references. They're very nice for running programs. So it's 49.985 degrees. We'll call it 50. We'll call it 50 degrees. Maybe I'll leave it. I don't know. Okay, so which I'm going to round to 50 degrees just for the sake of our sanity. Now, there's a problem. 50 degrees is not the angle, right? Because 50 degrees is always measured from the positive x-axis, which is over here. 50 degrees is this way, right? So if you imagine this vector going backwards, this is 50 degrees. Okay, so that is obviously the same as that. Right? So when you found 50 degrees, you're not finding the angle from the well, you are finding the angle from the positive x-axis, but it's related to this vector one. Okay, so how would I write the direction, right? And what angle is this? Well, the angle, right, so your direction is actually the 50 degrees, which is right here, plus 180 to get you all the way around. So 180 plus 50 makes 230 degrees. So the way we write that is 50 degrees south of due west. Or, well, let's think about it. If this is 50, then this must be 40. So, because they make 90. So you could say 40 degrees west of due south. Right? It's 50 degrees south of the left-hand axis here, or 40 degrees to the left of the south axis here. All of those are valid ways to write it. Although generally with direction, we want to have it written with compass headers.